Okay, gang, let's begin. Let's suppose I take a boulder and I take a sledgehammer and boom, I smash the boulder. Boom, I smash the boulder down into what? Rocks. And I take those rocks. Boom. Boom, I smash them down into
Sand.
stones.
Stones, okay.
Stones.
Okay.
Now I take a sledgehammer. Bam. Bam. I smash those stones down into
Gravel.
gravel. Come on, let's be a little imaginative here. Now I take that gravel. Smash. Smash. I break that gravel down into
Sand.
Sand.
fine gravel. Take that fine gravel, I smash that down into, begin with an S, end with an N. Try it. Sand. Now I'd be taking that sand, honey. I take that sledgehammer and I smash that sand down into
Dust.
dust, powder. Now I take that sledgehammer and I smash that dust down to
Atom.
Powder, fine dust.
fine dust. All right. Yay for all right, I take that fine dust and I smash that down into, begin with C, R-Y-S-T-A.
Crystals.
Crystals.
Crystals. Nice.
And I take those crystals and I smash those down into
Atom.
molecules, or begin with an A. And guess what we're going to be talking about today? Atoms, all right? Now I take those atoms and I smash those down. Can I break the atom down to finer still? Answer begin with a Y, end with a P. What is the answer? Yep, can do, okay? But I'll tell you what, when you get down to the atom, you are down to the elemental building block of matter. Turns out the atom can be divided too. But if you take matter like a hunk of gold and break it down, you'll finally come to one gold atom. Take a bar of aluminum, break it down, you'll come to one atom that is aluminum. Okay? It turns out atoms are the constituents of all matter. Take these atoms, ganging them together, and they begin with an M. Molecules, okay? But atoms are what we're going to talk about today. Atoms are big or atoms are small? Small or small? Small. We talk about how small atoms are. Anyway, we have all the atoms arranged in our textbook, open to the front cover, and you'll see the periodic table, the periodic chart of the elements. And there's the periodic chart, gang. You guys have got to memorize that by next time.
Easy.
Will you learn any physics at all if you do memorize that?
No.
You'll learn no physics. None. All you know is a lot of names and a lot of chart. Okay. But what is this chart? This chart is an enormous detective story to put this together. But what it does is it lists all the atoms by atomic number, starting off number 1 with hydrogen. Jump over to the page. Helium. Then lithium, beryllium, boron, carbon. What comes after carbon, gang? Guess which is heavier, carbon or nitrogen? Nitrogen. See, they keep getting heavier and heavier. Then oxygen, fluorine, neon, and so forth. Let's talk about those atoms. Okay, let's talk about some nomenclature for those atoms. Consider hydrogen. Hydrogen consists of a central nucleus, and it turns out I put that plus sign there because it's positively charged. And around that nucleus swarms a negatively charged particle called an electron. We're going to be talking more about this when we talk about electricity. This hydrogen has the chemical symbol H. Guess why? Hydrogen. Hydrogen, get it? Okay? And then we have numbers like this. These digits, this digit down here corresponds to the atomic number. That tells you the number of charges that are in the nucleus. That's 1. And this digit corresponds to the atomic mass. Over here, atomic number. And this one here, atomic mass.
No, they don't have it that way. That's totally good.
An atomic mass refers to the number of particles in the nucleus. We call these particles nucleons because sometimes you can have a neutral particle in there called a proton. And when you have that proton, this is still hydrogen. Turns out that positive nucleus, yes, Lee.
The neutral particle is a neutron,
What did I call it?
a proton.
Oh, did I call the neutral particle proton? I the first time in my whole career. I made a school. Yeah. Thanks, Lee. The neutral particle is a neutron. Guess why they call it neutron, gang? Neutral. Neutral. Come on, neutral. Guess how much charge it has? None. Okay? And it turns out this proton, which does has a positive charge, pulls on the electron and pulls it together. Later on, we get into electricity. We're going to learn the fundamental rule. And the fundamental rule just says this. Unlike charges attract, and like charges repel. And you know how come? Nobody knows. That's why we say it's fundamental. And we'll talk about that when we get to electricity. But we can just think of this electron being attracted to that proton in a way similar, in a way it's dissimilar too, but in a way similar to the way the Earth is attracted to the sun. That's a gravitational attraction. Here there's an electrical attraction. Anyway, that's a schematic diagram of the hydrogen atom. But this atom's got an extra neutron, so it has a mass of 2. Atomic mass of 2. This is heavy hydrogen. It's a little heavier. You see that? In fact, you can make water, H2O, where the H's are double weight hydrogen, and guess what we call the water?
Heavy water.
Heavy water. And you lift it up, you can feel it. It's heavier, okay? Heavier water. This is called an isotope of hydrogen called deuterium. Duet, duo, okay? Deuterium. You can also have another isotope of hydrogen which has an extra neutron. And these are relatively rare, especially this one. It's called tritium. Trio, 3 people, trio, tritium. And so this would be the isotope tritium of hydrogen. But see the one down there? That tells you that this nucleus has a positive charge of 1 and is capable of holding 1 electron in orbit to be stable. Okay? Now you know what happens if you add another proton? If you add another proton, now these 2 protons will pull this one tighter because there's more force. So what I'll do is pull that into a smaller orbit. And furthermore, hold an extra electron. This atom is physically smaller than the hydrogen. This atom with 2 protons is called, check your neighbor. Atomic number 2. Helium. That's helium, gang. Okay? That's helium. In fact, we have up here, we have 1, 2, 3, 4, so it's helium 4. And what am I going to put for the atomic number? 2. Helium, big or small? Small. Very, very small. You put some helium in a balloon. And you're going to save the balloon for next week when it's little Kathy's birthday, yeah? And next week comes, and where's your helium balloon? Is it on the ceiling anymore? It's on the floor. What happened to the helium? They got through the rubber. Why? Because it's a big, humongous atom? No, because it's tiny. It's tiny, honey. Get right through the little open spaces. Helium, the smallest atom that there is. I'll tell you another atom that's extremely small, too. A little bit bigger than helium. And that's fluorine. Ever heard of the element fluorine? You'd be having fluorine in your toothpaste, gang. And guess what the fluorine does to your teeth? You know what the hardest part of your body is? The hardest? The enamel of your teeth. And guess what's small enough to get right in between the atoms and hold them together strong, strong. Begin with the FL and with E. Try it. Fluorine. That's right. Fluorine. So you got fluoride toothpaste, yeah? That's what it does. It gets right in there. It gets in there. Makes it stronger. Nice to have fluorine in your toothpaste, ain't it, gang? Okay, makes your teeth stronger. Tiny atoms. If I put another proton in here, now I'll pull those things even tighter. And hold an extra electron, and that one will be out here. And that atom now is called, guess what? Lithium. Now it's lithium. Lithium 1, 2, 3, 4, 5. Lithium 5 and 1, 2, 3. What's the atomic number, gang? 3. And you keep going right up the periodic table. And then you come way up to what is the heaviest element found in large proportions in nature, and that happens to be uranium. And uranium has 92 protons, and most uranium has 238 nucleons. If I asked you people, hey, uranium, honey, 238 nucleons, how many of those nucleons are protons? And you gotta know. You would say 92. What if I said, how many nucleons in the nucleus? You would say
238.
238. Now, here's where you need your calculator. How many of those nucleons are neutrons? And you would say,
146.
well, you'd have to subtract, okay? You take this number, take away this number, and you'd have about 146, huh? You'd have 146 neutrons in that nucleus. So we have all the atoms which differ from one another principally by the number of protons in the nucleus. Because anything that has 3 protons
Rounded to this.
will hold 3 electrons, no matter how many extra neutrons you put in.
You round it to
And
this.
chemically, there's no difference between one isotope and another. Chemically, it has to do with this, mostly this atom here, how that is compared to these, the configuration. And so if you have 92 naturally occurring atoms, then you have 92 different patterns of levels of electrons. And you have then 92 different atoms with different properties. That's what we have, the elements. 92 through uranium. Got such thing? Now, atoms. Atoms are mostly empty. Because this is grossly exaggerated. I've drawn these very, very big compared to what this is. A better thing would be like if I draw the nucleus here, then out across the street the electron would be. The atom is as empty of matter as like the solar system is as empty of masses. You know, you got the sun, and you got Mercury, Venus, Mars, keep going out. If you got out in outer space, and you see the solar system down there, and you throw a dart, and let's suppose that dart doesn't respond to gravity. And you throw a dart and you want to hit either the sun, the earth, Venus, Mars, Pluto, If you want to hit one, what's your chances, big or small?
Very small.
Small, honey. The solar system is mostly emptiness. And only occasionally would there be a direct hit, even if you took showers and showers of particles, which didn't interact gravitationally now. If they interact gravitationally, they'll come right up and hit, yeah? But no gravity, they go right on by. Well, guess what, gang? There are neutral particles, thousands and thousands going right through my hand right now as I talk to you. Millions going right through my hand. And these neutral particles are from the cosmos. Okay? Most of them are neutrinos. Little teeny particles with guess how much charge, called neutrino? None, okay? They're smaller than neutrons. And those neutrinos are boom, flooding the universe. And these neutrinos are going right through, guess who? Us. You guys. Not me, but no, all of us. These neutrinos going right through and right out the other side without making a hit. You know why? Do you ever get the feeling some days that, I just don't feel like, I feel like I'm nothing. I'm nothing. I think I'm just nothing. You ever get that feeling? Guess what? I got news for you. You are nothing. Compared to the something, there's more nothing. Because the atoms that make you up are mostly, talk about being spongy. I mean, we're all sponges, honey. And most of the little particles take 133 million tons. It's several city blocks. Scrunch all those atoms up. 133 million tons. Scrunch them up until all these things here cave into one another. You get the size of a pea. So take the size of a pea and spread it out to city block city. That's how atoms are. Most of them. So these things go right through our body without ever making a direct hit. You get maybe one direct hit per year on the average. You walk, one got me. Okay, very, very seldom. Okay. Yeah. You know what? 1987, the supernova. Come on, huh? The supernova in the heavens, and showered the whole universe with neutrinos. And neutrino flux was so enormous that about 1 out of every 248 people, something like that, got one of those neutrinos, caught one. And the rest just went right through us, right through the other side. Never making a direct hit. Why? Because the space between the little particles of the atom are enormous compared to the size of the particular nucleons or electrons. Kind of neat, huh? So if there's a great big beam of neutrons coming right by here, you can just walk right through and they go right through the other side and register just as much on here whether you're in the beam or not. Yeah.
Wouldn't neutrons have more effects than neutrinos?
It turns out, I should say, a beam of neutrons, you would have more hits with a neutron than with a neutrino, but not too many more. You could walk through a neutron beam without harm. But I guess the counter reading will be a little less for neutrons. But with neutrinos, you get the whole class standing here. Hey, let me tell you what it is. It's a piece of lead. If you get a piece of lead thick enough, then it will stop half the neutrinos. How thick do you suppose the lead got to be? About this thick, this thick, this thick, this thick, as thick as the building, as thick as the world, as thick as like the diameter of the solar system, several light years thick. And guess what the answer is, gang?
6 light years, I think.
8 solid light years.
8 light years.
If you get 8 years thick of lead, that's how far something will go in 8 years. Light will go in 8 years. Get that thickness. Now put a beam of neutrinos through, half will come out the other side. So enormously, enormously transparent is even lead to such a thing as neutrinos, let alone us, huh? So we're mostly empty space, gang. Hey, if we're empty space, how about the chairs we're sitting on? Begin with ES.
Yes.
Try it. Empty space. How about your foot? Your foot's mostly empty space. I remember one time I went to a party, and at this party, the guy said this. I didn't know physics then. He said, you know what? If you keep kicking a wall, he said, oh, the reason your foot doesn't go through is because the atoms all... Did you ever take a couple of combs and go click, 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 click? And this dude said, if you keep kicking the wall long enough, pretty soon, your foot's going to get stuck. Because the atoms of the foot will line up with the empty spaces of the wall, and you can't get back out again. And I was really impressed about that. Wow, and I could have thought about that. But then later I happened to think, wait a minute. Now, if that's true, how about when people are walking along the rocks? I mean, there's never been a recorded case of someone, it's sunk in the rock, right? So why is it that we don't sink down through the chairs that we're sitting on? Why do you go like this? Why don't my hand go right on through? Like in the science fiction stories. Why? Why does it stop? How can I make contact with the table if this is mostly empty space and the table's mostly empty space? How many say, there's no explanation for that? There is an explanation, gang. You know what it is?
Electrical forces.
Oh, nobody be knowing. One be knowing. You guys didn't have a chance to read the book this weekend.
Celebrate.
Check the neighbor. Maybe you guys shy. See if the neighbor knows. Why is it you don't fall through your chair? Anyone have any ideas? Anyone? Trish?
Do the charges repel each other?
Yes, electrical charges. Right on. Wonderful, wonderful. Remember we talked about the atom here, these electrons repelling other electrons? Any electrons on your seat? Yes. Any electrons on your seat? Yes. And when these electrons squish closer and closer, what do they do? Begin with the R, end with tel. They repel. And there's an electrical repulsion, my friends, between you and the chairs upon which you sit. Let's put it this way. Let's suppose this table, pretend this table is a magnet. You guys know about magnets repelling? Turn them around, they attract, yeah? But you know magnets repel. You've all played with magnets. Wow, how come that happened? There's no reason for that. Come on, we'll talk about it later, yeah? Okay. But pretend that this table is a magnet. And pretend that my shoe here is a magnet. And I have a force of repulsion, magnetic repulsion between my shoes and the table. Can you picture in your mind's eye me walking across the table and not making contact such that someone could come up and take a piece of paper and slip it right into my shoe? Can you imagine that? Can you? How many people say, no, I can't imagine such a thing. You would have to show me. Show of hands. No, you can imagine. Hey, but you know what? Let me tell you. It turns out that's what's happening anyway. But it's not magnetism. Begin with E. Electrical. There's an electrical repulsion between you and the seat you're sitting on. And when you walk along the floor, it's an electrical repulsion that keeps you from oozing right down into the floor. These charges repel each other. In fact, at the atomic level, we talk about touch. I'm touching the table. But get right down to the realm of the atom. What's going on? Where's the touch? Does an electron bang into an electron? It turns out they get close and they get squashed. The electron, that atom gets squashed up a little bit. And the atom in your hand gets squashed up. And there's an enormous repulsion. And when you let go, you make that whole thing vibrate. Can you guys hear anything? Listen. You know what you're doing? I made those things, and the atom over the ear, all the way to your ear. We'll be talking about sound later. Physics, okay? But you make vibrations. You make the atoms vibrate. And that's what you do. You don't, the notion of touch is sort of like a lot different at the microscopic level. At the atomic, submicroscopic level, I should say. What do atoms look like? Let's suppose you took a microscope, you go to the chemistry part and say, give me an atom. Someone gives you an atom, you take some tweezers, you put it under the microscope, and you look at it. And you get a, what's it going to look like? Begin with an N, end with thing.
Yeah.
Nothing, right? Okay. Now you take another microscope and put it on the top of that microscope. Get 40 microscopes. Get on the top of a ladder. Every microscope in a microscope, you got look down, woo, what do you see? Nothing. Nothing. Then someone say, what's atom look like? And you say, got no looks. Atom got no looks. How can atom have no looks? It turned out an atom have no looks because it's smaller than the wavelength of light. That what you look at it with, huh? Yeah? Smaller than the wavelength of light. Let me show you what I mean. Let's suppose we have a tank of water here. And what I have here is I have like maybe a rock. There's a rock in the tank, and over here I have some sort of detector. And over here I take a meter stick and I go flip, 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 and I make waves, and the waves travel. Here's the waves like this. When the waves hit the rocks, can you see the rock disturbs the waves? With this detector, which consists of just a little thing there with a ping pong ball with a little arm that will float up and down, would this detector detect the presence of that rock? Would the waves come in differently to this detector if the rock weren't there? Yes. Can you kind of picture that in your mind? Okay. It turns out that rock would disturb the waves. That's because the rock is bigger than the waves. Here's the wavelength. Look at the size of the rock. Let's take the rock out of there. Now I have some blades of thin grass sticking up there, like this. These are very small compared to the wavelength of the waves. Now you you generate your waves. What's this going to get? Is this going to see the grass? It's not going to see the grass. Those waves go right on by the grass. The little shoots of grass are smaller than the wavelengths. This is not even going to pick it up. In the same way, little atoms about which you're made are smaller than the wavelengths of light. And so light can't pick up the presence of an atom. You can't see it. Light's too coarse. It turns out with a finer wavelength, you can get a wavelength that's very fine. Very fine wavelength, you can get an atom. And when I went to school, teacher types told me, we'll never see a photograph of an atom. Look in your book and we got one. You guys see that? What page? Whoever find it first, get an A.
180.
180. Lee, you already got your A. Who else had 180? You got an A too. See Troy at the end of the class, you'll be dismissed from all exams. Not quite. Page 180, gang. And there we have it, right there. And that photograph, gang, made some history. Because there are the individual atoms. The location of all those atoms, very clearly shown. That's taken with an electron microscope. Now there's new kind of microscopes that are called tunneling microscopes. And these microscopes give you a pattern that looks like this. We have a tunneling microscope right over in the physics department. And what that does, it takes a little needle that scans back, forth, across a surface of metal, and where the atoms are sticking up, makes a shorter path for the little electric current, and the little electric current is measured. It goes from the needle to the material itself, and all these little bumps show you the position of an atom. So we're really coming a long way. We can actually see where atoms are now. Because of what? Advances in technology. So now we know what atoms kind of look like. Not so much what they look like, but how they fix one to the other. So the guessing game that biologists used to have to do is greatly enhanced now. Now they know. Now we can do things with atoms. We can change the structure. We can change molecules. We can affect DNA, splice genes. Enormous things. Lee?
If all the parts of us that were made up of the atoms don't have and appearance. How come we have colors and appearances?
Yeah. Although one atom doesn't have an appearance, if I keep putting more and more, take one piece of grass. One piece of grass might not show anything here. Now I keep putting more and more and more and more and more all together, bunch them together, and pretty soon it starts to show. So although one won't show you any appearance, many will, because then they'll be on the order of the wavelength of light. And when you get larger than the wavelength of light, then the light will show their presence. Another thing, Brownian motion. You guys be reading about what Robert Brown did back in 1830? He's looking in a microscope. And in the microscope, he sees little things jiggling. And at first he thought it was something in there alive. There's little particles of soot. And these little things are jiggling. And Brown thought that maybe he saw atoms. But they weren't atoms. Guess what they were again? Little specks of dust banged into by, guess what? Atoms. It's like this. See this styrofoam cup? You guys can all see this. See this little BB right here? A little BB in my hand? I got a whole bunch of them there, see them? Spill them on the table. See all those BBs? You guys can't see those BBs because you're too far away from them, okay? But can you picture this? Can you picture the styrofoam cup on the table and all these BBs all moving around haphazardly, chaotically, and every once in a while more BBs hit one side of the cup than the other? What would the cup do? Wouldn't the cup start to jiggle? And you guys can see the cup, but you can't see what's making the cup jiggle. You know there's something smaller than you can see is making the cup jiggle. And that's what Robert Brown saw in his microscope. He saw little particles big enough to see jiggle. Why jiggling? Small enough. There could be more atoms on one side than the other. A little bit more net force on one side than the other. Boom, that thing will jiggle around. So in response to the jiggling atoms, boom, the visible observation, microscopic particles moving. Brownian motion. Turned out Albert Einstein explained that, and that was one of the first contributions of Einstein, to prove the existence of atoms. He showed that the motion of those little particles of dust corresponded exactly to the motion of atoms at various temperatures. I asked you before, atoms big or small? You guys said
Very small.
small, right? Okay. How small? Small. How big is the sun? How big?
Very big.
Big. And let me tell you this again. The atom is small, as many times small than us as the sun and average sized stars are bigger than us. So do you want something for your poetry class? Guess who stands between the atoms and the stars?
Us.
In size?
Us.
That's right in between. Human beings are as many times bigger than an atom as the stars are many times bigger than us. So they kind of give you a little bit of feeling. Here's another one. I like things like this. Apple. Any atoms in an apple?
Lots.
I said, well, it's a few, a couple of dozen. Come on, scads, right? About 10 to the 22, huh? Many atoms in an apple, okay? How many apples would fit in the world?
That many.
If you took the world and made it all hollow and you stuck apples in there, a lot of apples or a little?
Lots.
About as many apples would fill up the whole world as many atoms fill up the apple. So atoms are really small.
Minute.
Some people say no such thing as perpetual motion. Someone else say that's not true. Atoms are perpetually moving. They're moving all the time. Who's right? Are atoms in perpetual motion? Any atoms in this room? Yes. I'll be glad there's atoms in this room, right? They make up the air in this room, right? Are these air atoms moving? You come home from school, you're on one side of the house, Mom's on the other side of the house, she opens up the oven, there's a pie in there. You got that almost right away. How did you smell the pie? She opened the oven and what happened? Atoms, these things migrating all the time. So atoms are constantly migrating from one place to the other. Not only in the air, in liquids. To some extent in solids. Tiny extent in solids. But in liquids, certainly. Give you an example. Go home, your bathtub. Fill your bathtub high, huh? Take a eyedropper and take one drop of red ink. Tiny drop. You see the redness in there, yeah? But you see it start to spread out, right? That spreading out is evidence that the atoms are doing what? They're moving, right? They're migrating. They're going to spread out, spread out, spread out. Wait a little while. Go out for a couple hours. Come on back. Take an eyedropper. Go in that bed. Now you can't see the red, can you? It's all diluted, huh? You can't see it. Take your eyedropper. See if you can find a place in that bathtub that you can get a drop of water. Bring it up to the microscope and look at it and not have some ink in there. You ain't going to do it. That's going to spread out uniformly. You're not going to get it. That ink will spread out everywhere. In the same way, if you drop that ink in the ocean of the Earth, in the Earth's ocean, it will spread out too. When Christopher Columbus coming across the Atlantic Ocean, okay, if he had taken a glass, like a 6-ounce glass that you drink water, yeah? He'd reach down into the ocean and pick up that glass, and then take that water and throw it back in. Maybe tag it. Maybe tag it. Maybe make it all red or something. Or make it radioactive. Somehow you can tell later on. Today, that glass of water all mixed up, yeah? Long ago, yeah? Go to the ocean, dip up, hold it up to the light, son of a gun, a little pink. Because you know what? Some of the atoms in Christopher Columbus's glass are in that glass of water. There's so many atoms. All the bit about just throw a little DDT in here, it'll be okay. What do the penguins say about that way, way, way in the bottom of the world? Do they get the DDT? Yeah. They get the DDT on it. It's a visible amount of DDT is an enormous number of atoms. So they'll spread out. So you put a little pollution in the air, what happens? It takes about 6 years for that to spread out. I want everyone to do something today. I want you all to do this. Take a breath of air. Well, you don't have to, but go ahead. We take a breath of air, right? Did it feel a little musty? Do you know what you guys just did? You just breathed in billions and billions of atoms that once were exhaled by Leonardo da Vinci. The Italian type, yeah. Take another breath. That one was Einstein. Einstein, okay. Shakespeare. Hey, but do this. That one in Shakespeare. Go again. No? Do the same atoms come out that went in? No. What come out are different than the ones that went in. Why chlorides? Right? So every time you take a breath, you're breathing other people. And then when you breathe out, you're breathing out some of those people, and you're also breathing the most important person in the whole universe. And who's that?
Yourself.
Yourself. So some of yourself is all around the atmosphere. You guys know that? Now, let's do a little calculation. How many atoms are in your lungs at any moment with a normal-sized breath? It turns out to be about 10 to the 22 atoms. That's 1 followed by 22 zeros. 10 to the 22 atoms in your lungs at any moment. Get this! If you consider how many breathfuls of air are in the whole world, guess what the number turns out to be?
10 to the 22.
10 to the 22. So you know what that means, gang? There are as many breaths of air in the world as there are atoms in your lungs at any moment. How do we know how many breaths of air in the world? Well, what you do is you calculate the area of the world. You guys know what the area of a ball is? The area of a sphere? You know, anyone happen to know what the area of a ball is? A square? I mean, a sphere? Anyone happen to know what the area of a circle is? Take an orange and cut it in half and you make a wet mark, right? That's a circle. What's the area of a circle? Pi r squared. The area of a circle. Now, let me tell you something you'll always remember. If you know the area of a circle is pi r squared, you'll always remember what the area of a sphere is. And the area of a sphere is simply this. Take an orange, cut it in half. How many times could you take that wet orange and wet the outside of another that's the same size? Take a guess. Could you wet the other one at least twice?
Yeah.
Would the area of a ball be twice that? See? Take an orange, cut it in half. Now that's a circle, right? And that area is pi r squared. What's the area? See, this part here would wet this part here, right? That part be wet. Then you wet the... It turns out you could wet that 4 times. So that means the area of a sphere
4 pi.
equals 4 circles. 4 pi r squared. That's one way to look at it. Anyway, one can calculate the area of the world because we know what the radius of the world is. We can get the area. We know how deep the atmosphere is. Take the area, multiply by the depth of the atmosphere, and it's an average depth, and you get a number. You get a volume. And that volume is 10 to the 22 times as big as the volume of your lungs. That's wild. Because you know what that means, gang? I don't know if you guys can put this all together. But everyone do this. Now go like this. Now that particular breath that breath that you exhaled, atoms, right? Wait 6 years. Go to the other side of the world. Get with your friends, go. Guess what you got in that one breath? How many atoms in that breath you just guys let go 6 years in the next one? Begin with a W. 1. That's right. 1. So you 10 to the 22 atoms. And they're all going to spread out to 10 to the 22 liters, really. And every liter is going to have 1 atom. So anywhere you go, you pick up that 1. So any one person's, one breath, you guys got atoms from that breath right now. Now usually people take more than one breath. Leonardo da Vinci, honey, old dude, took many, many breaths. In all his breaths, you have hundreds of billions of atoms of Leonardo da Vinci's breath in you, or any other person who lived for a long time. So you were made up of the atoms of everyone who was ever before you. How many people in the world today? About 4.5 billion? That's 4.5 times 10 to the 9th. How many people compared to how many atoms in your lungs? Which is bigger? You notice a lot of people. People at 10 to the 9th. Atoms at 10 to the 22. How many people have been on the planet since the beginning? Nobody knows. But Arthur C. Clarke has made an estimation, and he said it this way: behind every human being stands 30 ghosts. That 1/30 of the all human race from way back is walking the earth today. That number's changing quickly. Let's say 1/30. So that means there are 30 more people on the earth from time 0 than there are now. Now there's about 4 billion. And there's 30 times that number for the total number of people that ever lived. 3 4s of 12. Call this 100. That's like 10 to the 11th. 10 to the 11th is 100 billion. So 100 billion people in the world. But the number of atoms in your lungs, 10 to the 22, what's that? Billion, 18. 10,000 billion atoms in your lungs. So many, many, many more atoms in your lungs than people that ever lived. So you can be rest assured that inside your lungs or inside your body at any moment are atoms from every human being who ever lived. You know how the Buddhists say things like, we are all one, we are all one. What do the physicers think about statements like that? The hardcore physicers, what do they say? It's true. It's true. Little kids know that we're all, they're taking a science class, learn that we're all made of the same kind of atoms. You know, there's like 92 different kinds, right? We're made of, No, but wait a minute, go a little further. We're not made of the same kind of atom. Honey, we're made of the exact same atoms, over and over again. Okay, Trish, I see you scratching your forehead there. When you scratch your forehead, whoop, a little forehead atom go out, right? Lee, you just went, okay? You just got a little bit of Trish. Now that'll become part of your ear. So part of your ear today would be part of Trisha's forehead yesterday. And you know what we're doing, gang? We are literally breathing each other. Because every time you breathe in, you're breathing something. Sometimes the atom gets stuck, yeah? They get stuck and they become you. So you're really part of everyone else. Yeah. Hey, someday you get down and out. Someday you get down and out. You ever have one of those days you don't feel like you're ever going to mount a darn thing? I just tell you what to do. On those days you get down and out, grab on yourself. Grab on. Say, man, I might have the blues today. But this that I'm holding on to, this is me. And this that I call me, that's atoms. And these atoms I'm holding on will live inside the bodies of everyone who's ever going to be on this earth. Because that's what happens to you. Your fate is to end up everyone else. True, false, or maybe?
True.
Think about that.